Hello everyone. Today we will consider fully developed laminar flow through parallel plate channel with uniform wall temperature. So, you have seen that in earlier classes we considered different cases with uniform wall heat flux boundary condition. In that case, if you remember, we have seen that temperature gradient with respect to x del T by del x is constant, as you have constant heat flux boundary condition. Hence, the second derivative of temperature with respect to x del 2 T by del x square is 0. That means, axial heat conduction was 0 for the case with uniform wall heat flux boundary condition. But today we are considering uniform wall temperature boundary condition. Hence, your axial heat conduction will not be 0. However, in this particular case we will make a special assumption that your axial heat conduction is very small compared to your radial heat transfer. So, we can neglect del 2 T by del x square, as del 2 T by del x square is much smaller than del 2 T by del y square. So, when we will consider uniform wall temperature boundary condition, we will neglect the axial heat conduction. So, it is the major assumption we are considering in today's class. So, you can see in this figure. So, we have parallel plate channel and we have uniform wall temperature boundary condition. X is the axial direction, y is measured from the center of the channel, and these two parallel plates are separated by a distance 2h. So, we are considering thermally fully developed and hydrodynamically fully developed condition. So, the assumptions are two dimensional steady incompressible laminar flow with constant properties, hydrodynamically fully developed flow. Okay. So, that means V will be 0, and thermally fully developed flow, uniform wall temperature condition we are considering, and this is the important assumptions we are making, that negligible axial heat conduction. That means, your del 2 T by del x square is much smaller than del 2 T by del y square. So, you can neglect the axial heat conduction, and also we are assuming that negligible viscous heat dissipation and no internal heat generation. So, now with these assumptions we will start with the energy equation and we will invoke these assumptions and make it simplified. So, energy equation is U del T by del x plus V del T by del y is equal to alpha thermal diffusivity del 2 T by del x square plus del 2 T by del y square. So, this is your energy equation. Now, we will invoke the assumptions like fully developed condition. So, V will be 0, okay, and your axial heat conduction is very small. So, this is also 0. So, you can write the simplified energy equation as U del T by del x is equal to alpha del 2 T by del y square. So, now we will consider one non-dimensional temperature and we will define with respect to the difference between the temperature of central line and the wall temperature. So, we will consider one non-dimensional temperature theta is equal to T minus T w divided by T c minus T w. So, T c is your central line temperature. Okay, so, T c is your central line temperature here. So, T c obviously is function of x, okay, but if you see the ratio T minus T w divided by T c minus T w is no longer function of x, it is only function of y. Okay. like we defined the non-dimensional temperature phi with respect to the mean temperature. So, similarly here we are defining another non-dimensional temperature theta, okay, with respect to T c minus T w. So, here theta will be function of y only, it will not vary along the axial direction. We are taking this non-dimensional temperature so that our calculation will be easier and it will be easy to calculate the Nusselt number. So, now from here you can see that your T you can write as T w plus theta into T c minus T w. Okay. So, del T by del x you can write as theta, T c is function of x only and T w is constant. So, d T c by d x. So, here T w is constant, right, and hence you can also take the derivative of t with respect to y del to t by del y square. So, you can write as, so now T c is function of x only and theta is function of y only. So, you can write T c minus T w into d 2 theta by dy square, okay, because theta is function of y, okay, and we are taking the second derivative of t with respect to y. So, it is T c minus T w d 2 theta by dy square. So, now you put these values in the energy equation. So, what you will get? Our energy equation is u del t by del x is equal to alpha del 2 t by del y square. Now, if you put these values you will get, and what is your fully developed velocity profile? Fully developed velocity profile for flow through parallel plate channel, it is u, which is function of y only, is equal to 3 by 2 mean velocity u m 1 minus y square by h square. Okay, for this configuration, okay, this is the mean velocity, okay, fully developed velocity profile. So, for this configuration this is the fully developed velocity profile and u m is the mean velocity. So, if you put all these things in this energy equation you will get 3 by 2 u m 1 minus y square by h square, then del t by del x, it is theta into d T c by dx is equal to alpha T c minus T w d 2 theta by d y square. So, now we will also non-dimensionalize the x coordinate and y coordinates. So, let us write x star as x by h and y star as y by h. Okay. So, if you put it in this equation, so what you are going to get? 3 by 2 u m 1 minus y star square I am writing, because y by h is equal to y star, then theta d T c, now this is x. So, it will be h in dx star is equal to alpha T c minus T w, and here you will get d 2 theta by now y square. So, it will be h square d y star square. Okay. So, if you rearrange it, so you can write as 3 by 2 u m, I will write 4 h, because we will define the Reynolds number based on the hydraulic diameter. In this case hydraulic diameter is 4 h divided by nu, I am multiplying nu, and right hand side alpha is there, I am dividing here by alpha. 4 h I have multiplied, I am dividing by 4 h, 1 by h is there, then you have 1 minus y star square theta d T c by dx star is equal to T c minus T w divided by h square d 2 theta by d y star square. Okay. So, now you see, so you can write 3 by 8 Now, this is Reynolds number based on hydraulic diameter 4h. Okay. Then nu by alpha is your non-dimensional number, Prandtl number. Okay. Then you have this h square, you can cancel with this h square. We have 1 minus y star square theta dTc by dx star is equal to Tc minus Tw d2 theta by dy star square. Okay. So, now we will separate the variables. Okay. So, we will put the which are function of x in the left hand side and which terms are function of y we will take in the right hand side. So, if you do that, then we can write as Re for h Prandtl number dTc by dx star divided by Tc minus Tw is equal to 8 by 3 1 minus y star square into theta d2 theta by dy star square. Now, you see the left hand side. So, left hand side your Tc is function of x only, okay. Tw is constant, Reynolds number is constant, Prandtl number is constant, okay. And also dTc by dx star is function of x only. So, in the left hand side is function of x only. Now, if you consider the right hand side, so if you see theta, theta is function of y only, and also d2 theta by dy square is function of y only. So, right hand side is function of y only. So, we have separated the variables, left hand side is function of x only, right hand side function of y only. So, this should be equal to some constant. Okay. So, now what constant we will take, whether is equal to plus minus lambda square. Okay. Now, whether you will take plus or minus. Okay. So, that we can see that we will use the rules of separation of variables method. Before that, let us write the boundary conditions. Okay. So, what are the boundary conditions? Boundary conditions are, you see, at y star is equal to 0, that means y is measured from the center line. So, y star is equal to 0 means at the center line. So, theta we have defined as T minus Tw divided by Tc minus Tw. So, at y star is equal to 0, obviously theta is equal to 1 because T is equal to Tc. Okay. So, theta is equal to, let us write y star is equal to 0, T is equal to Tc, hence your theta is equal to 1. Again you see that this problem is geometrically symmetric as well as thermally symmetric, because both the walls are maintained at constant wall temperature Tw, and from the center line both the plates are separated at a distance h. So, it is geometrically symmetric and thermally symmetric. So, maximum or minimum temperature will occur at the center line. That means, you can write d theta by or dt by dy will be 0. Okay. So, in this case you can write delta t by delta y will be 0 at y star is equal to 0, or you can write in terms of theta d theta by dy star will be 0. Okay. And at wall which is y star is equal to 1. Okay. So, obviously T is equal to Tw. So, theta will be 0. Now, you see the boundary conditions in y direction. So, at y star is equal to 0 at the center line, your d theta by dy star is equal to 0, and at t y star is equal to 1 on the wall, your theta is equal to 0. That means, you have homogeneous boundary conditions. Okay. So, both are homogeneous boundary conditions. Okay. So, that means y is your homogeneous direction. Okay. So, now let us consider this Sturm-Liouville boundary value problem. Okay. So, what it is? Sturm-Liouville boundary value problem. So, this is your second order differential equation. So, in this case if p x, q x and w x are real and boundary conditions at x equal to a and x equal to b are homogeneous, then you will get harmonic solutions in homogeneous directions. And in that direction, so you have to choose the value of lambda square such a way that in the homogeneous direction you get a harmonic solutions. So, now let us look back the equations. So, our equation, if you see, we have written R e for h Prandtl number dTc by dx star divided by Tc minus Tw is equal to 8 by 3 1 minus y star square theta d2 theta by dy star square equal to, now whether we will choose plus lambda square or minus lambda square. So, you have seen that the boundary conditions in y direction are homogeneous. So, that is the homogeneous direction, and we have to get the lambda square such a way that in y direction we get a Sturm-Liouville problem. So, that means if you choose this equal to minus lambda square, then what equation you will get? You will get d2 theta by dy star square plus 3 by 8 lambda square 1 minus y star square theta is equal to 0, and another equation you will get R e for h Prandtl number dTc by dx star is equal to minus lambda square dTc minus dw equal to minus lambda square Tc minus Tw. Now, you see this equation. So, now you can see, so if you compare with this Sturm-Liouville boundary value problem, you can see you have the weighting function w x as 1 minus y star square into 3 by 8, okay, and p x you can see it is 1 and q x is 0, okay, and y star is homogeneous direction. Okay. So, as y star is homogeneous direction and p, q, w are real, okay. So, you can have a periodic solution or harmonic solutions in y star direction. So, we have chosen minus lambda square to get the Sturm-Liouville boundary value problem in y star direction. Okay. So, now for this equation if you see, so integrate so what you will get? So, you can see, so you can write dTc divided by Tc minus Tw is equal to minus lambda square divided by Reynolds number into Prandtl number, okay, dx star. So, if you see, so you will get ln Tc minus Tw is equal to minus lambda square divided by Reynolds number x star plus some constant ln c, and you can write Tc which is function of x as Tw plus c into e to the power minus lambda square divided by Reynolds number for h into Prandtl number into x star. Okay. So, now we have to see the first equation. Okay. So, now we have to find the solution of this equation. Now, we want to find a series solution of this equation. Now, whether we can use the series solution for this particular second order differential equation? Let us see. So, when can we find series solution to differential equations? So, let us consider this differential equation, okay, second order differential equation p x d2 y by dx square plus q x dy by dx plus r x y is equal to 0. Now, we are just checking or when we can use the series solution, let us see. The x equal to x 0 is an ordinary point if provided both q x by p x and r x by p x are analytic at x equal to x 0. Analytic means that the function is infinitely differentiable, it is equal to its Taylor series centered at that point, at least in a region near that point. It means that these two quantities have Taylor series around x equal to x naught. We shall deal with coefficients that are polynomials. So, this will be equivalent to saying that p x 0 not equal to 0. So, the basic idea to finding a series solution to a differential equation is to assume that we can write the solution as a power series in the form y x is equal to n is equal to 0 to infinity a n x minus x naught to the power n, and you determine the coefficient a n. We will only be able to do this if the point x equal to x naught is an ordinary point. So, the above equation is a series solution at x equal to x naught. So, now for our problem let us see. So, if you compare our differential equation is this one. Okay. So, if you compare with this equation, you see p is equal to 1, q is equal to 0 and r is equal to 3 by 8 lambda square 1 minus y star square. Okay. So, now you can see that q by p and r by q are analytic. Okay. So, at x equal to 0 is an ordinary point. So, we can say that x equal to 0 is an ordinary point and we can have a series solution around y star is equal to 0 of the above equation as theta y star is equal to summation of n is equal to 0 to infinity C n y star to the power n. Okay. As y star is equal to 0 is an analytic point, because you have seen that q by p and r by p are analytic. So, we can find the solution of this equation as a series solution, and this series solution we will consider. So, our differential equation is d2 theta by dy star square, okay, plus 3 by 8 lambda square theta. The other term I have taken in the right hand side. So, 3 by 8 lambda square y star square theta. Okay. So, now the solution of the above equation in the form of an infinite series for the temperature is theta is equal to summation of n is equal to 0 to infinity C n y star to the power n. Okay. So, now let us take the derivative of theta. Okay. So, theta if you expand, what it is, C naught plus C 1 y star plus C 2 y star square plus C 3 y star cube plus C 4 y star 4 and so on plus C n y star n. Okay. Now, if you take the derivative with respect to y star, then d theta by dy star you can write as C 1 plus twice C 2 y star plus 3 C 3 y star square plus 4 C 4 y star cube plus so on plus n into C n y star to the power n minus 1 plus n plus 1 into C n plus 1 y star n, and d2 theta by dy star square, it will be twice C2 plus 3 into 2 C3 y star plus 4 into 3 C4 y star square plus so on plus n plus 1 C n plus 1 y star n minus 1 plus n plus 1. The next term if you write, so it will be plus n plus 2 into n plus 1 C n plus 2 y star to the power n. Okay. Now, you plug into this into the original differential equation. So, if you do that, plugging into the original equation, okay, we get, so it is d2 theta by dy star square. So, you write this d2 theta dy star square. So, it is 2 into 1 C2 plus 3 into 2 C3 y star plus 4 into 3 C4 y star square plus so on into n plus 2 n plus 1 C n plus 2 y star to the power 1. So, this is your d2 theta by dy star square. Then plus 3 by 8 lambda square into theta. So, theta is C naught plus C 1 y star plus C 2 y star square plus C 3 y star cube plus C 4 y star 4 and C n y star n. Okay. And in the right hand side now 3 by 8. So, the right hand side is 3 by 8 lambda square and y star square you multiply with theta. So, you will get C naught y star square plus C 1 y star cube plus, so C 2 y star 4 plus C 3 y star 5 plus C 4 y star 6 plus C n minus 2 y star n plus C n minus 1 y star n plus 1 and C n y star n plus 2. Okay. So, this is the right hand side. Okay. Now, what we will do? We will equate the equal power of y star. Okay. So, equating the equal powers of y star. Okay. So, if you see y star to the power 0, if you see its coefficient, so you can see here. So, this is your y star to the power 0, okay, 2 C 2 and then this one, and right hand side there is no term. So, it is equal to 0. So, you can write 2 into 1 C 2 plus 3 by 8 lambda square C naught is equal to 0. Then y star. Okay. So, if you see y star, so you have y star is 3 into 2 C 3 y star, here 3 by 8 lambda square C 1 y star. Okay. And in the right hand side we do not have any term associated with y star. So, you can write 3 into 2 C 3 plus 3 by 8 lambda square C 1 is equal to 0. Then y star square, you see y star square. So, this is the term 4 into 3 C 4 y star square, then here C2 y star square into 3 by 8 lambda square, and here you have the first term right hand side 3 by 8 lambda square C naught y star square. So, if you write the power of y star square, then you can write 4 into 3 C 4 plus 3 by 8 lambda square C 2 is equal to 3 by 8 lambda square C naught. Okay. So, similarly, you find the other powers, okay, the coefficient of other powers and equate it. So, just I am writing here y star to the power 3, you can write 5 into 4 C 5 plus 3 by 8 lambda square C 3 is equal to 3 by 8 lambda square C 1. And if you see y star to the power n, then you will can see n plus 2 into n plus 1 C n plus 2 plus 3 by 8 lambda square C n is equal to 3 by 8 lambda square C n minus 2. So, now let us apply the boundary conditions. Okay. So, applying boundary condition at y star is equal to 0, d theta by dy star is equal to 0. Okay. So, if d theta by dy star is equal to 0, you see from this equation, okay, this equation you see. So, if at y star is equal to 0, d theta by dy star is equal to 0, that means C 1 will be 0, because rest all other terms will become 0. So, C 1 will be 0. So, that means C 1 is 0. Now, you see here, if C 1 is 0, then from this equation, you see from this equation, if C 1 is 0, C 3 will become 0. Okay. Then if C 1 C 3 is 0, from here you can see C 1 C 3 are 0. So, C 5 will be 0. So, you can see all the odd coefficient C will be 0. So, that means you can write as C 1 is equal to 0, C 3 is equal to 0, as C 1 is equal to C 3 is equal to 0, C 5 is 0. Okay. So, all odd coefficients are 0. Okay. So, what we can write? We can write using n is equal to 2 m. From here you can see, from this equation you can write twice m plus 2 into twice m plus 1 C twice m plus 2, we are putting n is equal to 2 m, because all the odd coefficients are 0, plus 3 by 8 lambda square C 2 m is equal to 3 by 8 lambda square C 2 m minus 2. If you divide it, so you can write C 2 m plus 2 is equal to 3 by 8 lambda square divided by twice m plus 2 twice m plus 1, okay, into C twice m minus 2 minus C 2 m. Okay. Or we can write C 2 m is equal to 3 by 8 lambda square divided by twice m minus 1 C twice m minus 4 minus C twice m minus 2. So, you can see this equation is the recursion relation. Okay. So, it is for m greater than equal to 2. Okay. So, the above equation is called as recursion relation. Okay. If C naught is known, this equation allows us to determine the remaining coefficient. Recursively by putting n is equal to 0, 1, 2 and so on in succession. Okay. So, now let us write the temperature distribution. So, your temperature distribution theta, now you can write, because you know that odd coefficients are 0. So, m is equal to 0 to infinity C to m y star to the power 2 m, that means C naught plus C 2 into y star square plus C 4 y star to the power 4, C 6 y star to the power 6 and so on. Okay. So, that means you can write C 2 m, okay, where C 2 m is 3 by 8 lambda square by twice m minus 1 into C twice m minus 4 minus C twice m minus 2 for m greater than equal to 2, and the first equation if you see here. Okay, so, this is also valid 2 into 1 C 2 plus 3 by 8 lambda square C naught is equal to 0. Okay, so, this also we have. So, we also have 2 into 1 C 2 plus 3 by 8 lambda square C naught is equal to 0. So, if you see, if C naught is known, C 2 will be known, and if C 2 is known, then other terms will be known, because m for m greater than equal to, you can use this recursive relation. Okay. So, now invoke the other boundary condition. At y star is equal to 0, okay, you have theta is equal to 1. Okay. If y star is equal to 0, theta is equal to 1. So, you can see from this equation theta is equal to C naught plus C 2 y star square. So, these are all will become 0 at y star is equal to 0 and theta is equal to 1. So, C naught is equal to 1. Okay. So, if C naught is equal to 1, then you can write the value of C 2, okay, from this equation. Okay. So, C 2 will be minus 3 by 16 lambda square into C naught, and minus 3 by 16 lambda square into C naught is 1. So, it will be minus 3 by 16 into lambda square. Now, C naught C 2 are known. Now, you put this recursive relation and find C 4 and C 6. Okay. So, you can write C 4. So, if you put m is equal to 2, C 4 you can write as 3 by 8 lambda square 4 into 3 C naught minus C 2. Okay. C 2 and C naught you know. So, you can write lambda square. So, these 3 you can cancel. So, it is 32 1, okay, and C 2 is minus 3 by 16 lambda square. So, it will be plus 3 by 16 lambda square. So, you can write lambda square by 32 by plus 3. So, 16 into 32 into lambda to the power 4. Okay. Now, you put m is equal to 3. So, you can find C 6 as 3 by 8 lambda square 6 into 5 C 2 minus C 4. Okay. Now, C 4 already we have found here. So, it will be 2. So, it will be lambda square by 80, C 2 you put minus 3 by 16 lambda square, and C 4 you put now minus lambda square by 32 plus minus 3 by 16 into 32 lambda to the power 4. Okay. So, if you rearrange it, you will get minus 7 by 80 into 32 lambda to the power 4 minus 3 divided by 16 into 32 into 80 into lambda to the power 6. Okay. So, now let us apply the another boundary condition at y star is equal to 1, theta is equal to 0. Apply boundary condition at y star is equal to 1, theta is equal to 0. Okay. So, if you see theta expression, okay, so theta expression is this and y star is equal to 1, if you put this will become all 1. So, it is just C naught plus C 2 plus C 4 plus C 6 and so on. So, you will get C naught plus C 2 plus C 4 plus C 6 is equal to 0. Okay. Now, we will consider only the first 3 coefficients, okay. Other terms we will neglect. So, you can write C naught. So, C naught is 1. Okay. What is C 2? C 2 is 3 by 16 lambda square. C 4 this one. So, you can write lambda square by 32 plus 3 by 16 into 32 lambda to the power 4, then plus C 6. Okay, so, plus C 6. So, it will be minus 7 by 80 into 32 lambda to the power 4 minus 3 divided by 16 into 32 into 80 lambda to the power 6, okay, is equal to 0. So, you can see the denominator value 16 into 32 into 8, okay. So, it is a very high value. So, if you find, so this will become very small value. So, you neglect this term. Okay, as you have high value in denominator. Okay. So, if you neglect it, so rest you just rearrange. So, what you will get 1 minus 6 minus 1 divided by 32 into lambda square plus 15 minus 7 divided by 80 into 32 lambda to the power 4 is equal to 0. So, 1 minus 5 by 32 lambda square plus 8 divided by 80 into 32 lambda to the power 4 is equal to 0. So, it will be just 10. So, you can see it will be 1 minus 5 by 32 lambda square plus 1 by 320 lambda to the power 4 is equal to 0. So, you will get a quadratic equation lambda to the power 4 minus 50 lambda square plus 320 is equal to 0. So, that means your lambda square will be minus 50 plus minus root b square minus 4 ac, right. So, it will be 2500 minus 1280 divided by 2. So, that means you will have lambda square as 7.536 one value and another value will be 42.464. Okay. So, you will see that if you take lambda square is equal to 7.536, it will give physically correct temperature profile, but if you consider the lambda square is equal to 42.464, then it will not give a physically correct temperature value. So, you can neglect that. So, you just consider the value of lambda square as 7.536. So, the value of lambda square is equal to 7.536 will give the meaningful temperature profile. Okay, so, now we know the value of lambda square. So, if you put in the equation in the series solution, then you will get the temperature profile. So, in the series solution, if you see that you have found the value of C naught, then C2, C4 and C6. So, if you put this, so you will get the temperature profile. Now, next target is to find the Nusselt number. So, we will start from the governing equation. So, it is u del t by del x is equal to alpha del 2 t by delta y square, and if you remember theta we have defined as T minus C w divided by T c minus T w, and we have seen that del t by del x is equal to theta dt c by dx, okay, and dt c by dx star we have found as minus lambda square T c minus T w divided by Reynolds number into 4 h into Prandtl number. Hence, del t by del x, if you put all these, so you can see theta T c minus T w, okay, 1 by h into minus lambda square by Reynolds number into Prandtl number into T c minus T w. So, this is your del t by del x. Okay. So, if you put this value in the governing equation and alpha is equal to k by rho Cp, alpha is equal to k by rho Cp. Okay. So, now del t by del x you put it here, okay, and alpha you write k by rho Cp. So, you can see it will be rho Cp into u T minus T w divided by h, this you can cancel. So, it will be minus lambda square divided by Reynolds number rho um 4 h by mu, and this is your mu Cp by k is equal to k del 2 t by del y square. Okay. So, if you see, so rho Cp you can cancel, then mu will get cancelled, and now if you write it will be minus lambda square k by 4 h, okay. Then you can write ut divided by um into 2 h, okay, minus utw by um into 2 h. 2 h I am writing. So, 2 I have to just in the right hand side also I am dividing by 2, because here I have divided by 2, and you see this h is there and this 2 h I have taken. Okay. So, k by 2 del 2 t by del y square. Okay. So, now integrating the above equation from minus h to h. Okay. So, you see minus lambda square k by 4 h, you integrate it. So, minus h to h u t dy divided by um into 2 h, minus T w is constant. So, you can write minus h to h u dy divided by um into 2 h, okay, is equal to k by 2, and if you now take minus h to h, that you can write 2 0 to h del of del y del t by del y dy. So, this right hand side term you see the integration. So, this del t by del y at h, okay, at h. So, that will give you the wall heat flux, and del t by del y at y is equal to 0, it is central line temperature gradient, and that is equal to 0, because from boundary condition you have seen. So, you can write minus lambda square divided by 4 h k. Okay. Now, you see this term minus h to h ut dy divided by um into 2 h. So, that means it is your mean temperature, right, mean temperature definition. Okay. So, this is your mean temperature definition, and if you see this is minus h to h u dy. So, this is your um into 2 h, because this is the mean velocity into 2h. So, obviously this will get cancelled. So, you will get Tm minus Tw. So, you will get Tm minus Tw. So, we have written the definition of mean bulk mean temperature, and because we need to define the Nusselt number based on Tm minus Tw. So, it will be K del T by del y at y is equal to h, and it is nothing but Q double prime W. Okay. So, K del T by del y is Q double prime W. So, now you can see Q double prime W divided by T W minus T m. I have taken minus. So, this here. So, it will be 4 h by K is equal to lambda square. So, you can see it is h 4 h by K is equal to lambda square. So, that means, so Nusselt number based on hydraulic diameter 4 h is equal to lambda square, and lambda square value we have found as 7.536. Okay. So, we have seen that the Nusselt number based on the hydraulic diameter, for this problem the hydraulic diameter is 4 h is equal to lambda square, and lambda square we have already found. So, that is your 7.536. So, let us summarize. So, today we considered the fully developed laminar flow through parallel plate channels with constant wall temperature. We considered the non-dimensional temperature as T minus Tw divided by Tc minus Tw, where Tc is the central line temperature for easy calculation. From there we have found the separation of variables. We use the separation of variable method, and we have written the Sturm-Liouville problem because the boundary conditions are homogeneous in y star direction, and then we have found the solution of that governing equation using series solution, and from there we have found the values of lambda square, and then we found the Nusselt number starting from the governing equation, and Nusselt number we have defined with respect to Tw minus Tm, where Tm is the mean temperature, and you can see that for this particular case the Nusselt number is also constant, okay, independent of Reynolds number and the Prandtl number. So, you can see that for uniform wall temperature case, where you have the Tw as constant, Nusselt number is 7.54. In earlier lectures we have found with uniform wall heat flux, okay, for this flow through parallel plate channel we have found Nusselt number as 8.24, and if you see the temperature profile for this uniform wall temperature, okay, you can see the slope at the wall, okay, is lower than the temperature slope of uniform wall heat flux. Okay. So, if you see the temperature profile here, this slope is higher than this temperature profile, hence your Nusselt number is higher in case of uniform wall heat flux compared to uniform wall temperature, and there is almost 8.5% increase in heat transfer in case of uniform wall heat flux compared to uniform wall temperature. Thank you.